All right, good morning, guys. Happy Tuesday. I'm getting the days right. I'm slowly learning. Oh my God. All right, almost spring break. So today actually is going to be the last lecture for this chunk before the exam. So, I mean, unless something crazy happens and we can't finish these slides, we should be able to, but that means Thursday, we aren't going to have a class at 8 o'clock in the morning. We're still going to have the lab section. I promise this week's lab is going to be relatively quick compared to the last two, at least definitely quicker. But yeah, so just giving you a heads up for that. This is the last lecture for the exam, before the exam. So just looking at the schedule then, that means March 10th, we're not going to have a class. We will still have that lab section. So I'm sorry, Thursday crew, still got to show up, but you don't have to come to the lecture here this time in the morning. So yeah, this week we're going to be doing the sand cone test. It's going to be half like a calibration stage. And then the other half, we would normally go into the field and actually perform the test. But it's supposed to be like rainy and crappy all week. So I decided to just kind of make it a shortcut, like observation lab in the lab section. So that's why it should be a little bit quicker. But after this week, we're not going to have lab, I guess, for the next 3 weeks, not technically 2 weeks, because we have spring break, which is sweet. Spring break this year. And then the next 2 weeks after that, we'll have online like lectures posted because I'll be at a conference, and then we'll have our exam March 31st. So we won't have lab sections that week. So just want to put that on your radar. It's going to start winding down when it comes to the lab sections. Next week, or sorry, not next week, week 10. So March 22nd and March 24th, I'll be posting these online, like really short videos that overview these tools that you're going to be using for your final lab. So if you remember from the lab syllabus and what we were talking about, the final lab is like, I don't want to call it like a project, but it's an individual lab report where, very similar to the CE materials where you did like your own smaller report, you're going to be doing the same thing for this lab, but we're reviewing these geotechnical tools that are all online based and free to use and stuff that you'll definitely be using if you start working in geotech. So I wanted to show those two in 2 videos, March 22nd, March 24th. We're still on schedule for March 29th being the exam 2 review. I might post another video going over some of the homework solutions ahead of time, so you have more than just a few days to review that. So I'll keep you posted with that. But anyways, for the people just walking in, class Thursday, we're not having it in person. We're still having the lab section, but no in-person class Thursday at 8 a.m. Anything else on there that's important? Does anyone do anything fun for spring break besides work?
Work. Work is fun.
Utah, sweet. That's fun. Snowboarding or skiing then? Cool. Sweet. Okay, we'll get through all this stuff then. Soil permeability and seepage. That's what we're talking about today. We're sticking around in chapter 13:7. Last class, we talked about water movement through soil with my fun little cartoon that I drew here. Seepage, just to define some terms, seepage is the movement of liquid through the pore space of the soil. So we're talking about the actual like interconnected voids and the ability for water to flow through that interconnectedness and go from one side of the soil to the other. So permeability is a soil property, and it is a property that quantifies the ability of water to move through the soil. So again, what we're talking about a lot in geotech are we understand the physical behavior of soil, but what we do as engineers is quantify that using some number. So the number for permeability, which is shown by a K, we usually show this in length per time. That is what the units are in. So the soil property will have, like sand will have X centimeters per second or something like that. Diego.
So I know we usually haven't talking about water, but do we have to deal, I mean, for environmental stuff, still, do they have different permeability constants?
Yep. Yeah, exactly. Good point. I mentioned that maybe briefly last week. that, yeah, there's a term called hydraulic conductivity that's often associated with permeability. Hydraulic conductivity is normally the term used by hydrogeologic engineers and that kind of stuff, because we're talking specifically about water. But permeability is a kind of just a broad term for a specific type of liquid that has a set viscosity. So yeah, natural gas has a permeability through rock. Like bitumen has permeability through like a specific permeability. So that number, that permeability coefficient, is going to be dependent on the viscosity of the liquid, which we'll see in the labs coming up forward. We have to take the temperature of the water because that corresponds to the viscosity and the density, which then changes the permeability. So all of this is based off of our buddy Darcy and his law that states that the discharge velocity is proportional to the hydraulic gradient. So when you think of hydraulic gradient, just think of the energy that is applied. So this law kind of makes sense then. So the more energy that is applied to the water, the higher the velocity should be of the water flowing through it, right? But what he noticed was that depending on the soil type, or depending on the area that the water can flow through, that there is a factor that changes this relationship. So it's still a linear relationship, but the slope of that linear relationship changes based off of a bunch of things regarding the soil. So all of those like properties are combined into one thing, and that's K, and that is our permeability coefficient. So I is the hydraulic gradient. This is like, again, just kind of energy. Like if you think of energy. And then obviously we all know what velocity is. So physically, hopefully this makes sense. Like more energy, higher flow, higher velocity, but there's a term that is relating those two, and that's the permeability coefficient. So this is only valid for certain cases. So first, the soil has to be fully saturated. So S has to equal 100%, which means our VA, our volume of air, is equal to 0. So that's what we have to use to apply Darcy's law. If you think about it, like what we're assuming then here is if there were air bubbles in this soil, then those air bubbles will block the flow, and we wouldn't be able to define those pore spaces as a cross-sectional area of open channel flow. So we can't do that. So that's why we have to assume the soil is 100% saturated. The other thing is that flow is laminar. And that's going to be really important when we start talking about the seepage calculations here in a few slides. Laminar just meaning that the flow is the flow line. So the velocity vectors are all parallel to each other. So we don't have any crossing of streams, and that helps us like with the mathematical calculations or the analytical calculations. The other thing is that flow is steady. So you often called steady state, and continuous. That means the flow is not changing over time. So what the permeability is doing is taking like a little snapshot. But what we're assuming then is that that snapshot is continuous over a long period of time. So the flow is not like going up and down like very quickly. And then also we assume that water is incompressible. I mentioned this before, real world water is technically not 100% incompressible. If we put water in a pressure chamber and start applying pressure to it, it'll eventually turn into a vapor, and the volume is going to change. But we're assuming that in the states of pressure that we're dealing with underground, that water is staying incompressible. So as we apply load to it, as we apply energy to it, the volume doesn't change. That's basically what that is saying. So for Darcy's law, how to illustrate this would be like, I provide this example here. And like what we're actually physically saying with the Darcy's law is that if we have a plot of velocity versus the energy on the x-axis, like you see in this little, really small image on the top left, that will be a linear relationship. So as we increase the energy, we will have an equal increase in velocity. But the slope of that line is going to be dependent on a bunch of physical characteristics of the soil. So like the void space, the packing density, the amount of fines, all of these things. But that slope is characterized as the permeability. So that slope is equal to that permeability coefficient, K. We also talked about how what we are measuring coming out of the soil is the discharge velocity. But if we were to somehow zoom into this individual pore spaces of the soil, what would be occurring is what we call the seepage velocity. And a lot of times the seepage velocity is an important controlling design parameter, because that seepage velocity is going to be what causes erosion or causes, or is going to be one of the design characteristics or considerations, because we need the soil to take a certain, or the water to take a certain time between point A and point B of soil or something like that. So seepage velocity is where that porosity term comes in handy again. Porosity is that volume of voids divided by the total volume. So that is what we talked about way back in the beginning of the class, and this is where it's an important property for that again. And hopefully this makes sense. The seepage velocity should be higher than the discharge velocity. As if you remember from from hydraulics class or whatever, that Q is equal to AV. So if we're assuming Q, the flow rate is staying the same because it's continuous. If we decrease the cross-sectional area, what should happen to the velocity? Should increase, right? Like you could probably picture that, like if, I don't know, if you've ever been on like a river, like a kayaking on a river or something, when the river is super wide, it's usually really nice and slow, but as soon as the river starts getting skinnier, then the velocity of the water increases and you're going really fast on your little kayak and stuff. So same thing on a super, super small scale with soil. Like as it's flowing through a tube, an open tube, that flow rate is staying consistent, but the velocity is slower. And then as soon as those water molecules have to travel through the pore space of soil, it's going to have to speed up to maintain that law of continuity. So that's why that discharge or seepage velocity is usually higher than our discharge. So usually I'll just draw this here. Usually higher than our discharge. So this is just the Darcy's law here for this equation is just like a 2D representation. Remember though, if what we're talking about most of the time is a 3D representation of it. So in the 3D world, which we're all living in, then instead of a velocity, we would care about the flow rate. So the flow rate being a cubic meter of volume of water per second or per time. And that's going to equal the velocity times that cross-sectional area. So since we already have that function for velocity, then we can put that in with K equals I, or V equals Ki. So Q equals Kia, and that's cross-sectional area and all that fun stuff what we went over before. So ultimately, what we're able to do by deriving these here is show a function of the velocity times the cross-sectional area is equal to the area of the voids. And this is used here to start deriving our tests that we're going to be, or the equations that we use for our tests to calculate the permeability coefficient. So this is also a recap, showed these pictures before, but these are just some of the real applications of why we need the permeability coefficient. Like a lot of times, especially in Florida, we want to design soil to either let water flow through it quickly, if we want to control flooding in that way, or on the other side of things, if we want to control flooding, we want water to not flow through the soil. So usually we have these two extremes of permeability that we care about. Lake Okeechobee is a good example of these earth dams that were installed around the entire perimeter of the dam. And inside that dam, they have this clay core. And the contractor needs to ensure that this clay core has a set permeability so water does not flow through it and flood everything on the other end. So what we see on both ends of it is that flow is controlled by the energy, or what we call head. And this is always in like feet of water or meter of water or something like that. So in your open channel flow, the Bernoulli equation, the total head should look something like this equation. Hopefully it looks familiar to you guys. But in soil, we just show it as this. So we assume that in soil, the velocity is so small through the pore space that that is a negligible term. So the v squared divided by 2g, that velocity head, is negligible, and we can remove it for soil. So that means we only have a function of two things when we're looking at the Bernoulli equation in soil. It's the elevation head, which is shown by Z, and then the pressure head, which is shown by the pore water pressure divided by the unit weight of water. So let's look at an example here. So I know these pictures are kind of like creepy looking, like look like these like spiders or something like coming out of it. But you know, these are, you should get used to like seeing these types of images, because this is really big for the FE, PE, and also your other classes too. So again, just to recap what these little tubes are telling us sticking out, this is showing the total head basically at whatever point that tube is in the soil. So if we were like, picture these as just like a straw, like sticking into I don't know, like a can or something. So if we have the water elevation shown here, and water level shown here, and we stick a tube right here at point B, then of course we should expect it to rise up to the same elevation head or the same pressure head there, right? Same with point C down here, right? But now here with point D, we see a lower head, and then point F, we see a lower head. So that means what is happening here compared to point B to point F? Which direction is the water wanting to flow? From F to A or A to F? A to F, yeah, because there's more energy here, so that means the water wants to flow this way, right? So for the total head, again, in soils, we have two considerations. So our HZ is going to be the elevation head. The HZ is just based off of whatever datum you want. So like for this case, it says this is the datum right here. That's fine. But if you wanted to change it and put F as the datum, that's fine. If you wanted to put A as the datum, that's fine. As long as the datum stays consistent, this elevation head will balance out with each other. So just keep that in mind. The main important thing is the pressure head. But the elevation head, as long as you're consistent, you just choose a random datum and you're good. So the datum is basically just saying where Z is equal to 0. So let's look at these points here for B, C, D, and F. And let's first find our total head. And we can do that based off of the manometers, or those tubes sticking out. That's what's telling us our total head. So our total heads here at F is going to be 0, because it's going to be right at our datum, right? So this tube is just poking up right at our datum. So that's H is equal to 0. At D, we have 7.5 plus 12.5, right? So right here, gosh, whatever. This is at D, right at here, this is 20. And then at C and B, we have 40, since that's what this whole thing is here. So that's our total head, and this is all in centimeters. So now elevation head, this is all just based off of our datum. So our elevation head, this is our HZ. Our total head, this is our H, or it could be HT if you want, whatever that is. So for our elevation head, since our point F right here, this is actually at -5. since our datum is above it. So we have to go down 5 centimeters to get to our elevation head. Our point D, this is 7.5, right? Because it's 7.5 up from our datum. Point C is 20, since it's 20 up from our datum. And then point B is 35, since that's all the way up from there. So now we know that we have only these three terms here. Our total head is equal to our pressure head plus our elevation head. So we can also find our pressure head. And we should know that all of these should be equal to each other. So what we're looking for now for our pressure head, that's how much the water rises up in the tube itself. So our pressure head in this example would be this, HP. Oh my gosh, the dead spot on my laptop is growing. This would be HP. All right, hopefully you guys get the idea before it disappears, but that's how much the tube actually rises up. So for this first one, this is 5. For the second one, this is 12.5. Third one here, that's 20. And then the fifth one is 5 centimeters. So theoretically, all of these should add up to each other, right? This is based off of our total head equation here. So let's just double check here. So if we actually add all these up, what we'll see here is for point B, this makes sense. For point C, this makes sense. But for point D, we actually have a value that is different in between these two. Or sorry, head loss, no, yeah. So these all should add up. 7.5 plus 12.5, there we go. 5 plus 5, 0. So these all check out. So our total head loss or change between these two from point A to point F. So this head loss is A to F. So can we find the permeability coefficient from that? So how would we actually find this? We need velocities in this case for the permeability coefficient. We can find the hydraulic gradients, but for the permeability coefficient, let's just say we keep increasing the flow, the velocity of water at the top to 10 centimeters per second, and we can measure that. So our hydraulic gradient, I, is our delta H over L. So the L again is the length of the soil of where the water is traveling. So this would be our L here. So this is equal to our hydraulic gradient then would be equal to 1.6. And what we have to check here is that the units are the same. So make sure that they're all in the same units so they cancel out. So our permeability coefficient is just our velocity divided by our hydraulic gradient. So our velocity is at a steady 10 centimeters per second. So we can find our permeability coefficient this way. So a permeability coefficient of our soil would be 6.25 centimeters per second.
Questions like that, like two drawings, the drawings.
No, yeah, you need to know the tubes, at least at some certain points. So like, that's a good question. So right here at point D, you don't technically need to know that point, right? You don't need to know that tube. What we assume is that it's always linearly interpolated between those two. So like you could draw as many tubes as you need to for this, but it would always follow this linear interpolation. Sorry, those colors, there's too much colors there, but it would always follow like a linear in between the 2 points. So yeah, you always need to be given at least 2 pressures. So you need to know at least these or this, and then you should be able to interpolate between the 2. Okay, so this would be like how, this is kind of showing like how we would actually calculate the permeability coefficient in the lab. Yeah.
How do you do that?
So the head loss is, I should have used a different term here. This head loss is from point A to point F. So if we're starting at point A and we have this much energy or this much head, like how much is being lost at each point? So when it comes at point B and point C, we have the same number, right? So there's like, we're not losing anything, but as the water is traveling through the soil, we're losing energy. So from point A to point F, we have 40 centimeters of loss. And you can see that that makes sense by just looking at this difference here. So this is 40 centimeters. So I should have used a different term, because if you've taken fluid mechanics, head loss, you're probably used to that term as like, you know, bending in pipes and like, you know, head loss due to friction and all that stuff. Technically, that is what's happening here. Like we're losing energy, but it's a different, like it's not as hard. We don't follow those like special calculations for like 45-degree elbow and pipe and all that stuff. It's just taken automatically from the energy heads. Yeah.
So the total head, we find that with the elevation and pressure, but is that just, did you just put it in there like after you found that, or did you like know, was that before you?
The pressure head?
Yeah.
Yeah, so you can find it that way, but you could also see the pressure head physically by how much the water rises up in the tube. So yes, it's the same thing, but you can find it, since we know the total head and the elevation head. There's only one more term, you can subtract those two, or by just looking at the figure here. Again, this is, I'm just going to erase all this stuff so it's kind of clear. Our pressure head, so I'm just going to say this is HP here in purple. Our HP is this. This is how much the water actually rises up by itself. And that, like, this is kind of like illustrating the whole equation here, because if this is our HZ here, our elevation head, then it would make sense that our total head is HZ plus HP. Let me use a different color. That's so is that making sense there? So we have the total head, and then that's combined of 2 points. So you could technically see the pressure head just by how much the water rises up in the tube.
The elevation is just to this tube, but the pressure is to the top of the
Yep.
water.
Yeah, so the elevation is just based off of whatever datum you choose. So you might not always be given a datum. You can use your own datum and the math will always check out. You know, like in this case, it just says use the datum at point E. But if you decided to use point A as a datum or point F as a datum, anything, as long as it stays consistent in all of your calculations, then you're good. Okay, I'll make sure to include some more examples. Actually, I think on your homework, there's an example like similar to this that will hopefully be a little bit less messy. Sorry for all the colors and all that stuff. All right, so let's talk about how we actually find it in the lab. There are two methods to determine the permeability coefficient in the lab. One is called constant head test and one is called the falling head test. What happened here? Come on. So the main reason we use these two different types of tests are dependent on the soil type. So constant head test and falling head test are used on just two types of soil. And you can probably guess which one based off of, or like the differentiation between this based off of the generalized range of permeability. So constant head test is used for coarse grain soil or soil that is expected to have a high permeability. And then our falling head test is used on soil that has a lower permeability. So our fine grain, our sand, or our like silts and our clays. So for the constant head test, K is computed based on the volume of fluid passing through the sample. So this requires steady state flow. So this means that the flow rate is not changing over time. That's all that fancy math equation is showing. The change of flow divided by the change of time is equal to 0. So the flow rate, the change of flow rate is not changing, it's steady. This is only valid if the soil allows a sufficient amount of flow. So if we took a clay sample, like remember from our Atterberg tests, if you pour water on that clay, what would happen to it? Like the water would just beat on top of it, right? You needed to actually mix into it. So we cannot do these constant head tests on samples that are low permeability. So they're only used for like, ooh, let me change this color here, for coarse grain soil. Like our sand and gravel. So we would not be able to like physically do the constant head permeability test on silts or clays or anything that has a very low permeability, because the flow would be so low because the water, like the soil is not absorbing, it's not taking up the material. So on the other side of things, the falling head test, the K, the permeability coefficient, is computed based on the flow or the fluid flowing into the sample. So it's not a steady state condition. We have transient flow into the sample. So that means the flow rate is changing. We don't have a constant steady stream of water going through the sample. We have a specific head of water, and then we measure the time it takes for it to fall through the sample. So this is really good for soil with low permeability. And this is like silts and clays. But even compacted sands will do this. So the falling head test, you wouldn't be able to do this test on gravel or like loose sands, but if we compact the sand and it's like well-graded sand and it has a low permeability, then we can still do this test. So let's look at some pictures of what it actually looks like. So for the constant head test, we'll be doing this lab after spring break and after our exam too. But what we use is what's called a permeameter. You may have seen these things, permeameter. What they do is allow water to flow in through the top and flow out the bottom, and then we can put soil samples in between that. And basically what we have to have is a constant head or a constant elevation of water flowing through it. So who knows what like a weir is from classes that aren't this class, weir. So a job of a weir is to keep like a lake elevation at a certain height, right? Like, so when the water flows up too high in a lake or a pond, then this weir is like a kind of like a block that then when the water flows up above that, it'll pour over the edge. So basically what we're doing with this test is creating a little mini weir. So we need the water to stay at a certain elevation. So if we do that, we just have this edge here and we keep pouring water into this tank, and then we allow it to overflow like that, like when you're thawing out chicken and you have like the chicken in there and you just keep the cycle going so the chicken doesn't get nasty. So it's the same thing scientifically. So what we do then is when we have this constant head, we then put a soil sample through these two permeable stones, like, you know, it's just to keep the soils from eroding out of the sample. And then we measure that flow that is traveling through the sample. So the flow rate of the water is just the volume divided by time. So what we're actually doing is just measuring the volume that is flowing out of the sample over a certain amount of time. So it's easy to measure volume of water. We have beakers, we can measure the weight of water. So what we'll do is we'll just stick the beaker under the out effluent for like 30 seconds. And then if we have that volume, we divide it by 30, we have the flow rate. So what we have with this, since we know, let me go to a different color again. Since we know from Darcy's, our flow is equal to our KIA, our KIA, which is the permeability coefficient times the hydraulic gradient times the cross-sectional area. Our permeability coefficient is what we want to find here. So we solve for it like this. Q is IA. Our I is our hydraulic gradient, which is our change in head divided by the length. And what we know is if we have a constant head here, so this is constant. And if we have an effluent or another head here that is constant, then our delta H is staying the same. So that's what that little tiny thing is showing there, delta H. And we can physically measure the length of our soil that the water is flowing through. So we have the water is entering here and then it's trickling through the soil and flowing out. So we can find our hydraulic gradient just by taking these measurements. So we know our delta H and we know our L, so we find our hydraulic gradient. We can also measure our cross-sectional area because this is technically a tube, right? This is like a cylinder. So we can measure that cross-sectional area. And then we can measure the flow. So we have all of those things. So what the equation actually looks like is we have the permeability coefficient, which is what we need to find, is equal to the volume times the length divided by the time times the change in head times the cross-sectional area. So all this equation is just these two combined together. That's all this is. It's just, since we're dividing by a fraction, we just move the values up and so on and so forth. And then the flow rate is volume divided by time, right? So Q. So that's where that VT is coming from in there. So this is a really, really easy test for the lab that we can then determine our permeability. And the benefit of this test is, if you remember from our compaction test that we were doing, or that we were talking about and that we did in CE materials lab, the purpose of the compaction test is to determine the optimum moisture content and the maximum dry density. And the purpose of that is to recreate the conditions in the field. So what we can do now is compact the sample to the same void ratio in our permeameter and then run this test. So now we can actually find the permeability of our field conditions here easily in the lab, just from that void ratio and that energy applied. So, but as like we said before, and as Diego mentioned, the K is dependent on the viscosity of the fluid. So in our case as geotechnical engineers, in this class at least, we're always going to be just focusing on water. But a lot of times, like salt water is going to have a different like permeability coefficient. You know, groundwater pollutants may have a different permeability coefficient. So you would have to measure the viscosity of the fluid. And for water, it's easy. For the other stuff, it's hard to do. So that's why we're just sticking with water. That's the constant head test. Our falling head test is very similar, but a little different. So with this, we look at our Q in and we assume that it is the same as our Q out, which is equal to KIA. So remember, for our falling head test, we don't have steady state, we have transient flow, which means our change in flow over time is equal to something. It's not equal to 0. So this derivation of this equation is a little bit more in depth. I'm not going to go through the whole thing, but I'll show it here. So this is our derivation for the permeability coefficient using the using the falling head test. So you cannot use this equation for the constant head test. And you'll see it's a function of two H's, so H1 and H2. What do you notice is not in here compared to the first one? Starts with a V, the volume. So we are not actually measuring the volume of the sample or the volume of the water leaving, which is kind of beneficial, because if you think about the constant head test, what we're doing is like physically taking a beaker, sticking it underneath the effluent, and then looking at our watch. And then as soon as it hits 30 seconds, moving the beaker out. there's a lot of room for mistakes in that area. Like if you're not quick enough, the water could spill out. So it's all dependent on that physical measuring of the fluid or the flow leaving our sample. For this, we don't worry about the water leaving our sample. As long as we know the energy difference, the head difference between the two and the time, then we're good to go. So we use the same equipment, it's just set up a little differently. Our area, our capital A is the area of the permeameter, but then we have a lowercase a, which is the area of this standpipe feeding the permeameter. So we actually have a smaller pipe that is feeding our permeameter, and then we have our larger permeameter here. So this is our big area, and then this is our little area. So T is the time it takes for head to fall from H1 to H2. So again, what we do this sample on is what we do this test on is a low permeability sample. So this head is falling like relatively slow through the sample. It's not, if it was a super permeable sample, then it would just like fall super quick. But this is falling nice and slow, so we can easily count if we know we count the time it takes for the head to fall from like one point to the other point, our H1 and H2. So what we're technically doing is finding the velocity that way. So just like before though, the K is dependent on viscosity, so we still need to take the water temperature and all that stuff. But the important thing to note about this one is there's no need to measure the volume out of the fluid. And this is really beneficial because when we start thinking about like field permeability tests. So in this test, again, like we're not taking a beaker and we're not sticking it under the effluent and counting to 10 and then moving away really quickly. All of it is included in the equation. So let's look at these two equations next to each other. So again, falling head test, use this equation, and we see that the permeability coefficient, K, which we want to find, is a function of the heads and time. For the constant head, it is a function of volume, change in head, and time as well. So this volume really plays into a role of when we're actually talking about the in situ field hydraulic conductivity. So if we were to do this test, if we need something much more accurate and we want to know the permeability of like a clay layer at our project site, how we would actually do this test, we couldn't do the constant head test because we can't calculate or we can't measure the flow rate coming out of the soil, 60 feet down. So what we would actually do is they'd drill a pipe or drill a hole down to this layer, and they'd fill it up with water. And then this would be our H1 or this would be our H2. We then fill this up to another elevation and then count the time it takes for it to flow back down to its initial state. So this right there is our falling head test, right? Because we don't need the flow rate coming out of our sample. So the falling head test is really beneficial because that's how we can actually find the in situ field permeability, as well as the in-class, in laboratory field permeability. There's a few other like types of permeability tests that can be performed in situ. So like determining the actual permeability coefficient in the field. The Boutwell permeameter is one. There's another one that's called like the VIP, the vertical in situ permeameter, that FDOT uses a lot. So if you work around in Florida, you may have to use that. It was developed by like UF a few years ago. So it's still like starting to be used a lot. The Boutwell permeameter, you don't really need to know too much about it, but it follows this equation here. But the issue with this is we can't control the K direction. So we can't get a actual horizontal or vertical permeability. The flow of water leaving this could go any direction we want, right? So we're not getting a nice straight like vertical permeability coefficient versus horizontal permeability coefficient. So one of the most beneficial ways to determine the actual permeability coefficient in the field is doing what we call drawdown tests. So these require pumping and observation wells. So they require like large sites. These are usually only used for like like large like landfills and other types of things. You wouldn't have enough space to do this on like a Wawa or like a smaller project site. But basically what we do is we first drill a primary borehole. And then what we want is this permeability coefficient of our sand. So let's just say we want that of our sand. So we'll have this primary borehole, and then we'll also drill at least 2 observation boreholes. So you need to drill, geez, I can't talk, at least 2. You can't just have one, you need to at least have 2. So if our groundwater table is at that location and this is a sandy aquifer, after we drill these holes, we should expect the water to rise up to this height, right? And I should say, like, these aren't just like open boreholes. Like, these would be filled with casing, and then the casing will have holes drilled into it to allow water to flow through. And then we'll apply a mesh around the outside of it so it allows water to go through, but not soil to fall and plug in those holes. So that's what these boreholes are actually looking like. So what we can actually do then with this primary borehole, take a pump that doesn't look like that. It's like a legit pump. And we pump the water out, and we can measure the flow rate that is taking out of this hole, right? So what would we expect if we were pumping water out of here? What would happen to the water elevation in this borehole? It should go down, right? So we should see that as we are pumping this, we have a drawdown because the energy, we're sucking energy out of it. So the total head, the energy is going down. And we see that physically through the rate here. So what we'll see in these observation boreholes is we see an effect from this primary borehole pumping. We aren't doing anything with these observation boreholes. We're just looking at them. So they'll usually have like sensors at the bottom of them to measure how much water is above them and not. So we see they're affected to it. And as you probably imagine, the further away we go from the point that is sucking, the less we feel it, right? So what they actually see is that this follows a cone of depression that would look like this. And this cone of depression can be mathematically defined. And if we know the permeability coefficient, or if we see that this cone of depression, how much the water is, or like basically the slope of this cone of depression is dependent on the permeability coefficient. So I'm not going through all the derivations, but we have this equation that is then used to define this. So it requires 2 boreholes or 2 observation boreholes. So our R1 and our R2, which is the radius away from the borehole, the primary borehole. And then our H1 and our H2, which is the heads. And this head usually is taken from like an impermeable layer. So they would usually drill this down into like a clay layer or some layer that has a permeability coefficient that is much, much less than the one that we are trying to find. Much, much less. So this is a really common test, but again, this requires a lot of space and time. So these are really only used on like large scale projects where you need to like quantify the full groundwater regime. So like, anything issues with groundwater pollutants like landfills, you would usually have to do some of these tests. And the good thing is once you drill these observation boreholes, they usually keep them open, and then they can continuously take samples of water from that to test for different types of pollutants and that stuff like later on down the line. So I remember seeing a question like this on the FE. There wasn't anything on the PE, but you'll see this equation like this, and then usually they'll give you some like cross-section analysis that looks like that, but you actually would need to calculate the H2 and H1 based off of like what it looks like, or they'll give you the permeability coefficient and you need to calculate for it. Something like that. All right, so let's get into seepage analysis a little bit. So seepage analysis is important because this is actually looking at the stresses that are attributed to flowing water through the pore space. And this is important because if we don't control the seepage, then if we have too much flow, then we can have erosion or piping, or we can have failure and flooding. So this is like heavy on the geotech side of things. So we have different like types of techniques to mitigate or slow down the seepage. And basically what we're trying to do is increase the length of our that the water takes to flow. So we have what's like a seepage force, which is the hydraulic gradient multiplied by the unit weight of water. So this isn't the exact seepage force like calculation, but this is like the proportional to. So generally, like when we're talking about a large scale, like 2D sense, this is the values for seepage force that we would actually measure. So if we remember, the hydraulic gradient is the change in head divided by the length, right? Now, a lot of times this change of head, this delta H, is hard to control because this would be like, you know, the natural conditions, like the elevation of a lake versus the groundwater table. Like if we can't, it's easier, it's hard to control the elevation of the lake or the groundwater table. But what we can control is this L. So if we increase the L, we are decreasing the hydraulic gradient, right? Because it's on the denominator, it's on the bottom side of the fraction. So if we increase this L and require this water to travel further to dissipate the same amount of energy, the same amount of delta H, then we will subsequently be slowing down and lowering the seepage force. That's why, like in these two examples, like this could be like the natural case. We see the water traveling is like this L right here, right? Like it's unimpeded, it can just travel that way. That's the length that the water travels. Now, if we install what we call a slurry wall, in this case, like this is a layer that is impermeable. So this could be like clay or concrete. Now this water, to get to the other side and balance out, needs to go all the way down here and back up this way. So now this L is much, much larger than the natural case. So as we increase that L, now we are decreasing our hydraulic gradient, which means we are decreasing our seepage force, which is good for us because then there's less likelihood of internal erosion and that kind of stuff. So most of the time when we do seepage analysis now, since we have nice computers that are nice and helpful, we use a numerical modeling software. So with these numerical modeling, since it's all based off of like an easy analytical, like a relatively easy mathematical equation, these are pretty accurate and they are able to calculate and estimate the flow coming through soil at a pretty high amount of precision. So this numerical modeling, this is like an example of a 2D earth dam. And you know, basically what you're showing here is you have this soil, it's a homogeneous soil, or you could change it to whatever you want. So it's a constant K. That K value is known. And then we have the water elevation on one side, the water elevation on the other side. So what we basically have is this delta H here. And then the length is like automatically calculated from your geometry. And then you can find like the seepage and the stress analysis for that. There's still an old school technique though, that is still used today to verify these numerical modeling. And this is an analytical solution. And this is the graphical solution. You have a question? Oh. Of Laplace's equation. Does anyone know what Laplace's equation is? Yeah, it's a differential equation thing. So there's a lot of like fun math involved to it. So it's derived from Darcy's law. It's going to be harmless, I promise. It's derived from Darcy's law, but what we're looking at is only in one direction. So Darcy's law, that's why I'm putting those little subsets X's in this case. So the velocity in the X direction is equal to this permeability coefficient in the X direction times the hydraulic gradient. So that hydraulic gradient, when we're looking at it only in one direction, we use these fancy things to impress our friends that are just delts. So this little tiny backwards looking D, delt H, that's just saying the change in H in one direction is divided by the change of X. And that's technically the same thing as our hydraulic gradient, right? Now from our continuity equation, we also know that the flow in is equal to the flow out. So what we do with this, looking at the flow is just equal to the change of velocity divided by the distance. For the X direction and the Y direction, we have this equation, and that is our Laplace equation, which I'm not going to get into all the details for that. So we can combine these two, and by actually plugging it in, the Darcy's law to the continuity equation, we have this one. So what this is actually physically telling us, or first, I guess we have some these are some of the conditions that we are assuming for all of these. Basically, what this produces is a equation that represents a family of curves. So there's two curves that can be divided into two groups in this 2D space. So we're only looking at it in 2D space. And what we have are flow curves and what we call equipotential curves. So flow curves are the physically, if we had it tracked a water molecule, the path that this one water molecule is taking as it's flowing through the soil. So luckily, since we are assuming laminar flow, what does that mean about these two soil particles? Like if we took one here and one here, there's two water molecules, what would we expect to happen? They would always stay parallel to each other. They'd never cross because it's not turbulent flow. The equipotential curves, what these curves are just telling us are these points at which energy is dropping. So we're having head loss, and equi meaning equal. It's just where an equal amount of energy is dropping. So that's all these two are showing. So that what we could actually visualize this as is if we had a condition like this, where this is kind of tricky to look at because it's a weird color, but you know, this is like all water here. And this is all water here. So this is like the ground surface elevation here. That's the ground surface here. So basically what we're saying is like we have a flow line. So if we tracked one water molecule right here, it would follow this path until it got to the other side. And then these equipotential lines are where we have equivalent amounts of energy. So what we'll see is that it's actually combined with multiple flow lines. So if we had a water molecule here, it would follow this path. If we had a water molecule here, it would follow that path. Here, it would follow that path. And we could technically subdivide this into as many lines as we wanted, right? But for this, there's these equipotential lines. For every drop here, like if we added one here, we would have to add another equipotential line. So this is a graphical solution, which means it's an estimate. It's a graphical solution of the Laplace's equation. And what we call these are called flow nets. You guys cover this in other classes at all? Flow nets. So what they're actually looking at here is we can draw these by hand, but we have to follow two rules. One, there always has to be a 90-degree intersection of the flow lines with the equipotential lines. So obviously this is really hard to do, but these should always be perpendicular to each other. Also, what we want to see is these flow elements need to follow a box shape. So usually what I'd like to do is like see that you can draw a circle in each one of these intersection lines. My professor in college said you always wanted to draw circles, not zucchinis. So you don't want to have like a zucchini like that, even though zucchinis are different, I guess, but whatever. So you want to be able to draw these circles. So obviously there's a lot of room for error for this, but as long as we can graphically like get it close then if we count the number of flow lines and the number of equipotential drops, what we'll see is that this is proportional to the permeability coefficient and the overall seepage through it. So I'm going to go through a little bit more derivation here. It's not going to be too scary. We'll go kind of quick. But what we're actually looking at is if we zoom in on every single one of these little tiny boxes, every single one of these flow elements, what we should see is that the flow in is equal to the flow out. So the change of flow is equal to each one, but then at each single element, we have this change of flow is equal to our K equals IA. So this is from our Darcy's law. So this is in 2D. So that means if we were just looking at like one box, then the change would be equal to this delta H divided by the D. So the D here is the length. Now it's 2D, so we need that length to multiply by an area. So what we're actually multiplying it by is this C, or like, to get the actual area of it. What we're assuming is that this is like a little 2D representation like of a box. So I don't know how to really draw that, but imagine this being like a little box or something. So the flow is entering this way and then leaving out that way. So all of these flow cells should be squared. So that means this D is equal to our C, and our F is equal to our E, A is equal to B. So all of these little proportions here are equal to each other. So if that's the case, then our change of flow going through each individual cell is just equal to this K value times the change of head going through each one. So that means if we can find our change of flow through one of them by looking at our total head divided by the number of drops. So that ND value is the number of these flow lines that we go through. So if we want to find, this is our change of flow in one cell. If we want to find our change of flow all of the cells, then we need to multiply it by the total number of flow channels. So the total number NF, which is our flow channels. So NF here is equal to number of flow channels. And then our ND is equal to number of equipotential drops. So for this example here, our number of flow channels, we would have 1, 2, and 3. So these are our flow channels. So 1, 2, and 3. So for the equipotential drops, we would have 1, 2, 3, and 4. So that would be our ND is equal to 4. So theoretically, we could add more flow channels, but if we add more flow channels, then we need to add more NDs. We need to add more drops too, because we need to keep these elements in a square shape. So let's look at a quick example. So something like this, if we have something like this, you could theoretically draw a flow net. And I think in your homework, I have you guys drawing a flow net. On the exam, I am not going to make you draw a flow net, but you need to at least be able to interpolate these because it's really difficult to draw these things. Like, it's like we can start with usually like one, or you usually start with trying to discretize them this way, like trying to look to get them as parallel as possible. But you can see that once we start drawing these flow lines, it gets a little tricky because we need them to always be square shape and we need them to intersect perpendicular to each other. So in this case, this isn't even a square, but it's difficult to get it exactly. So then for the second flow line, we would need to keep it square-like. See, so even just right there, should probably be a little bit deeper. So something like this. So these would be really difficult to actually draw. You can probably still squeeze one more in here, and you'd probably have to like separate this with another one, you know, something like that. Moral of the story is we have computers now which help with this. But in order, you will still need to learn how to read these things. So for this, in this specific ratio, what we would have is how many we would have 1, 2, 3, and then 4. So we would have 4 flow paths. And then the number of equipotential drops, we would have 1, I guess for this, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would have ND is equal to 10. And then we could plug that into our equation to get our flow. So if our total flow coming through it would be our permeability coefficient times our change in head divided by our number of drops times our number of flow lines. So the change in head would be this section here. So you could physically like see the difference between that. So the more drops we have, the lower this ratio of NF divided by ND, that ratio there, the more drops we have per flow line, then the lower our flow should be, right? Because this ratio, the smaller it is, the low, like we're multiplying this by a smaller number. So let's just see, like, for example, then like using a cutoff wall or something. So in this case, they added this dam here. We still have the same amount of section. If we were to draw another flow line or try to draw another like amount of pipes, this one, we always start at a vertical line here. Draw something like this. Yeah, this is tricky. So ultimately, what we would see is by the addition of this cutoff wall, even though these flow lines do not look good, we would be subsequently increasing the number of drops. Whatever, this should actually be squares. This is really hard to draw these things, but we'd be increasing the number of drops and keeping these flow channels the same. So for 4 now we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we have ND is 11. 1, 2, 3, 4. And flow is equal to 4. So this ratio NF divided by N11 is now lower. So we should see a lower amount of flow. Let's look at an example. Again, as I said, you're not going to be required to draw them for the test. I don't think for the PE you'd ever really, or the FE you'd need to draw it either, just because it's a really tricky thing. But you need to at least be able to understand what we're looking at when we see a flow net. So we have this figure, and it's shown below: flow net cross-sectional area of a dam that is 600 feet long. So that's important. So this dam is going in the the out of paper direction, like this direction here, 600 feet. So like it's going in and out of the paper 600 feet. So assuming that it has a uniform cross section, what is the total seepage rate under the dam? So we're looking at just a little slice of the dam and it's coming out of the paper 600 feet. So we're given the hydraulic conductivities, or the permeability, sorry, in inches per second. So to find the flow rate, we know the flow rate is equal to, these are isotropic conditions. So these are our flow channels and our equal potential drops are here. So our flow rate is equal to this equation from our flow nets. So we have the permeability coefficient and we have the flow net. So all we need to do is count the number of flow channels and the number of equipotential drops. So for our flow channels, we have 1, 2, 3, and 4. And then to make sure I didn't already do that, all of these other things we know, we just need to keep track of the units. So for our NF, we have 4. For our equipotential drops, we have, I'll just do it from the bottom. So 1, 2, 3, 4, 5, 6, 7, 8. So we can calculate what we need from this equation. So our Q is our permeability coefficient, so times 10 to the minus 4 inches per second, times our delta H. Our delta H is 50 feet. So 50 feet, but then we need to convert this into inches. And then our N is going to be 4. Sorry, this should be 8. So our NF is 4. And then we divide it by our ND, which is 8. And what we'll see, since we're in the correct units here now, is our Q is sorry, I did it in feet per squared per. Let me put it in feet instead. Everything in feet. So 12 inches is 1 foot. So that would cancel these inches. And now we're in feet squared per second. It's 0.00. Sorry, one more 0. Sorry, guys. Feet squared per second. So let's just say we wanted to put this in like units that made more sense to us, like cubic feet per day. So yeah, per foot of dam. So if we have a total length of dam is 600 feet, then our Q would be this is only for 1 foot, so we'd multiply it by the total length of dam. And whatever that value is, we then convert it into seconds to days. And what we'll see is Q is equal to 4320 cubic foot per day. So you can see how if we have the flow rate, let's say they were actually able to measure the flow coming out of here, right? If we measured the flow coming out of here, then we could also back calculate and determine the permeability of this soil too. So you can see like how like in real world conditions, most of the time that's the case. Like we can actually put a pump and we see the water coming out. And if we measure the flow leaving, then we can back calculate and find the permeability of that. So one more thing to note with this, these equipotential drops, what each one of these flow channels is technically telling us is that it's a change of head equal to each other through each channel. So our total change of head for this is what? 50 feet, right? So from point A to point B, we have a change of head delta H of 50 feet. So each one of these drops, we are losing the same amount of head. So if there are 8, then delta head per drop is equal to 50 divided by 8, right? You can see that. So each one of these little drops, if we wanted to find the head right here, halfway through the point, the total energy head right there, then how many drops do we have? We have 1, 2, 3, 4 drops. So that means we would have an equal amount of energy dropping through each one. So we can find the delta H per drop and then multiply that by 4, and that would be what it was. But what you'll see is that's generally going to be a linear interpolation between those two, if we draw the diagram correctly. Okay, so that was it for the soil permeability. So this is not true. We still have lab on Thursday, but hope you guys enjoy your spring break. If I don't see you before that, we do not have lecture Thursday, 8 a.m., but we still have lab. See you guys in lab. Yes, there is a quiz this week.